All right, let's take a look at the practice test. For the instructions, we're asked to evaluate each. All right, let's take a look at the first problem. So here we have log base 343 of 1/7. So what is this equal to? In other words, this right here is the exponent that is required on this base of 343 to get an answer, or you could say a result of 1/7. I'm just going to set this equal to x since we don't know what it is. And then I'm going to write this in exponential form. So I'm going to say that this is my base, so 343. This would be raised to the power of x. So that's my exponent. And then this would be equal to this argument for the logarithm, which is 1/7. So we need to figure out what is the value for x that's going to make this true. Well, what you can do here, since you have a 343 here, and you notice you have a 7 here, well, 343 is really 7 cubed. It's 7 times 7, which is 49, then times 7 again, which is 343. So you could say that this is 7 cubed raised to the power of x, and this equals, for 1/7, you could write that as 7 to the power of -1. So here you could use your power to power rule. 7 stays the same, and then you're just going to multiply the exponents. So 3 times x is 3x, and this equals, here you'd have 7 to the power of -1. At this point, you have the same base on each side. So you have this 7 and this 7. And so we can use our rule that we talked about earlier on in the course, where basically we just set the exponents equal to each other and we solve the resulting equation. So 3x is equal to -1. And make this a little bit better there. We would divide both sides of the equation by 3. So we can isolate x. This cancels, and you get x is equal to -1/3. And let me get rid of this. So I'm going to, in the place of x, say this equals -1/3. Now it's very easy to check this if you want. Again, just put it into exponential form. You would say 343, that's going to be your base. It's going to be raised to, this right here is your exponent. So -1/3. And this should be equal to, again, the argument for the logarithm. So this is 1/7. So how would we determine if these two sides are the same? Well, again, on the left here, all you really have to do is use your rules of exponents and say that this would be 1/343 raised to the 1/3 power. All you're doing is you're going to take this and drag it across the fraction bar and change the sign of the exponent. So that's where that's coming from. Does this equal 1/7? Yes, it does. This right here is the cube root of 343. So let me put this down here. This would be 1/the cube root of 343 is equal to 1/7. And we should know that the cube root of 343 is 7. So let me come down here and say that this would be 1/7 is equal to 1/7. So yeah, our answer here, which is -1/3, is correct. Okay, let's take a look at problem 2. So here we have log base 3 of 1/81. Again, you could just say that this is equal to x. Would put this into exponential form. So the 3 is the base, and this would be raised to, your exponent is x, and this would be equal to the argument for the logarithm, which is 1/81. So for this one, what I would do is write 1/81 as 3 to the power of -4. In other words, this right here, let me do a new line so nobody's lost. I could write as 1/3 to the 4th power. And again, this 3 to the power of x would stay the same over here. Let me just drag this up here. Now I would say this is 3 to the power of x is equal to, you drag this across the fraction bar, you change the sign of the exponent. So this is 3 to the power of -4. And of course, at this point, because you have 3 here and 3 here, you could just set those exponents equal, and you would have x is equal to -4. So that just tells me that this right here is going to be -4. Let me erase all this so I can put this in frame. So let me say that this is equal to -4. And this one's really easy to check. You would have 3 to the power of -4 is equal to 1/81, which we know is true. This is, if you go through it, 1/3 to the 4th power is equal to 1/81. And of course, this would be 1/81 is equal to 1/81. So our answer here, -4, is correct. All right, let's take a look at problem 3. So here we have log base 5 of 1/125. So again, what am I going to do here? I'm just going to set this equal to x, since it's unknown at this point. Again, you could just put this into exponential form. So 5 to the power of x would be equal to this argument for the logarithm, 1/125. So 5 to the power of x is equal to 1/125. Now, most of you know that 125 is going to be 5 cubed. It's 5 times 5, which is 25, times 5 again, which is 125. So let me go ahead and write this as 5 to the power of x is equal to 1/5 cubed. And again, you can drag this across the fraction bar. You just have to change the sign of the exponent. So I'm just going to say that this is 5 to the power of x is equal to, we'll have 5 to the power of -3. So at this point, again, you have a 5 here and a 5 here. So that same base, you're just going to set those exponents equal to each other. So you're just going to say that x is equal to negative 3. So that's going to be the answer here, just negative 3. So let's say that log base 5 of 1 over 125 is going to be equal to negative 3. Now again, in terms of checking it, you just go back into exponential form. You would say 5 raised to the power of negative 3. So this raised to this power is equal to 1 over 125. Is that true? Yes. This right here turns into 1 over 5 cubed is equal to 1 over 125. And of course, you get 1 over 125 is equal to 1 over 125. So the answer of negative 3 is correct. All right, let's take a look at problem 4. So here we have log base 4 of 64. And so again, I'm just going to set this equal to x. And then we're going to say 4 to the power of x. Again, just doing this. So this is my base. This is my exponent. That would be equal to 64. Now, most of you can eyeball that and see it's going to be 3 because 4 cubed would be 64. But again, you can just write 64 in terms of having a common base with 4. So you could say 4 to the power of x is equal to, we know this would be 4 cubed. And then because this right here, this base of 4 is the same as this base of 4, you can just simply say that now the exponents would be set equal to each other. So x is just equal to 3. So let me get rid of this and just say that this would be 3 here. And of course, this is really, really easy to check. You would just say that 4 cubed, so 4 cubed would be equal to 64, and of course it is. You would get 64 is equal to 64, which is a true statement. So this guy is going to be 3. All right, for the next few problems, we want to solve each equation, and these are going to be very simple equations, similar to what we set up for the first 4 problems. So for problem 5, we have log base x of 6 is equal to 1/3. Okay, so all we have to do again is just write this in exponential form. So x raised to the power of 1/3 would be equal to 6. X raised to the power of 1/3 is equal to 6. Okay, now I have this x here, and it's being raised to the 1/3 power, or we're taking the cube root of it. So basically, how do we undo that? Well, we're going to cube both sides. Let me slide down here a little bit, and I'm just going to cube this side and cube this side. So let me put an exponent of 3 and an exponent of 3. So basically, by the power to power rule, we know that x would stay the same. 1/3 times 3 is 1. So now I just have x by itself. And this equals 6 cubed is going to be 216. Again, if you want to check these, you can. You would be saying that log, let me put this off to the side, log base 216 of 6 is equal to 1/3. In other words, 216 raised to the power of 1/3, or the cube root of 216, would be equal to 6, and that's a true statement. This would give you 6 is equal to 6, so this is a valid solution. X is equal to 216. Okay, let's look at problem 6. Here we have log base 4 of x is equal to 2. So again, to put this into exponential form, you'd have 4 squared is equal to x. So we know that 4 squared is just 16. So we would say x is equal to 16. Now again, checking this is very, very straightforward. Let me move this over here like this. You would have log base 4 of, just plug in a 16 for x. Does this equal to, where you're saying 4 squared, does that equal 16? Yes, it does. So this x equals 16 is a valid solution. Okay, for problem 7, we have log base 3 of 243, and this is equal to x. So again, to put this into exponential form, 3 to the power of x is equal to 243. So 3 to the power of x is equal to 243. And again, for this one, 243, a lot of you will know that's 3 to the 5th power. 3 times 3 is 9. 9 times 3 is 27. 27 times 3 is 81. And then 81 times 3 is 243. So this you could just write as 3 to the 5th power. And then you could just set your exponents equal to each other. So x would just be equal to 5. So let me put that over here. I'll just put a little border and say x is equal to 5. And of course, if you want to check that, you would say log base 3 of 243 is equal to 5. So this is 3 to the 5th power. 3 to the 5th power is equal to 243. And that's a true statement. You would get 243 is equal to 243. So this x equals 5 is a valid solution. All right, for problem 8, we have log base 6 of negative 36 is equal to x. So this problem obviously has no solution, and that's because this right here is creating something that's undefined. When we work with a logarithm, we want to make sure that the argument is positive. So it can't be 0 and it can't be negative. If you try to set this up in exponential form, you have 6 raised to the power of x is equal to negative 36. Well, that has no solution. right? If you take this 6 right here and you raise it to some real number, let's say it's negative, 0, or positive, it doesn't matter. You're always going to get something that's positive. You can never get 0, and you can never get something that's negative. So let me just erase this and say that there's no solution. So there's no solution. All right, for problem 9, we have 5 minus 9 log base 5 of negative 4x minus 1, and this equals 14. Okay, so the idea here is we're just going to isolate this guy right here on one side and have a number on the other, and then we can just put it into exponential form. Now we're going to see more advanced logarithmic equations later on. For right now, these are pretty easy, and you just follow that format. So we're going to subtract 5 away from each side of the equation. This would cancel. We get negative 9. We have log base 5 of negative 4x minus 1, and this equals 14 minus 5 is going to be 9. Let me divide both sides of the equation by negative 9. And so what's going to happen is this would cancel with this, and we're going to have log base 5 of negative 4x minus 1, and this equals, so if we do 9 over negative 9, that's going to give me negative 1. So let's write negative 1 over here. Let me slide down a little bit. And now we can put this into exponential form. So this is your base, this is your exponent, and it's going to be equal to this right here, the argument for the logarithm. So 5 to the power of negative 1 is going to be equal to negative 4x minus 1. Now this right here is 1/5, so you could write it that way if you want. Let me write 1/5 here. And to clear that fraction, I'm just going to multiply both sides by 5. And so 5 times 1/5 is 1. You could show that as canceling if you want. So this equals, this needs to be distributed to each guy inside the parentheses. So 5 times negative 4x is negative 20x. And then 5 times negative 1 is negative 5. Okay, at this point, let me go ahead and add 5 to both sides of the equation. So this would cancel. 1 plus 5 is 6. So you're going to get negative 20x is equal to 6. Let me divide both sides of the equation by negative 20. So this would cancel. You get x is equal to positive over negative is negative. If I think about 6 and 20, let me rewrite 6 as 3 times 2. And let me rewrite 20 as 10 times 2. And of course, you can cancel a common factor of 2 between numerator and denominator. So this would be negative 3/10. All right, let's write out x equals negative 3/10. And let's just make sure we got the right answer. So that's going to get plugged in right there. So you have 5 minus 9 log base 5 of negative 4 times negative 3/10, and then minus 1, and this should be equal to 14. So let me write this out. 5 minus 9 log base 5 of, here negative times negative is positive, and basically, let me just cancel those away like that. If you think about 4 and 10, there's a common factor of 2. So 4 divided by 2 is 2, 10 divided by 2 is 5. So let's say this would be 2 times 3, which is 6 over 5. So this would be 6/5 minus 1. Let's write that as 5/5. And this should be equal to 14. Okay, let's come down here a little bit, and let's see what we have. So let me write 5 minus 9 log base 5 of. 6/5 minus 5/5 is 1/5. And then this equals 14. So what we see is log base 5 of 1/5. Now, we have not talked about the properties of logarithms yet. That's coming up in the next lesson. But there's a property that we can use here to make this very, very quick. If you have something like log base 5 of, let's say, 5 raised to the power of negative 1, then what happens is this exponent right here can come out in front as multiplication. In other words, something like, let's say, log base a of x to the power of r is equal to r times log base a of x. So this is called the power rule for logarithms, and we'll talk about this in the next lesson. So for right now, let's use this and say this would be equal to, you can bring the negative 1 out in front as multiplication, and then it's times log base 5 of 5. And so log base 5 of 5 is 1. So you would basically have, let me get rid of this. Let me move this over here like this. You would basically have negative 1 times 1, which is negative 1. So this right here can be replaced with negative 1. Let me get rid of this, and let me write that you would have 5, let me go plus negative 9, and then times negative 1, and this equals 14. Well, negative 9 times negative 1 is positive 9, so this is 5 plus 9 equals 14, and you get 14 equals 14. So that solution, which was x is equal to negative 3/10, is going to be correct. Okay, for problem 10, we have 4 log base 4 of negative 3x minus 6, then minus 3, and this equals 9. So again, I want to isolate this right here to get the problem started. So that will be equal to some number. Then you can put it into exponential form and you can solve. So let me go ahead and add 3 to both sides of the equation. This cancels. We get 4 log base 4 of negative 3x minus 6. And this equals 9 plus 3 is 12. Okay, at this point, let me divide both sides of the equation by 4. And we'll say that this is going to cancel. And we'll say log base 4 of negative 3x minus 6 is equal to 12 over 4 is going to be 3. Okay, at this point, you can put it into exponential form. So we're going to say 4 to the power of 3, or 4 cubed, is equal to, we'll use the argument from the logarithm, so negative 3x minus 6. We know 4 cubed is 64, so let's go ahead and write negative 3x minus 6 is equal to 64. At this point, let's add 6 to both sides of the equation. Let's slide down here. This would cancel. You get negative 3x is equal to 64 plus 6 is going to be 70. So let's divide both sides of the equation by negative 3. This would cancel. You're going to get x is equal to negative 70 thirds. Now 3 is a prime number and 70 is going to be 7 times 5 times 2. So there's really not anything you can do to simplify there. So this is your answer. All right, so we found that x was equal to negative 70 thirds. Let's plug that in for x right there and make sure that we get a true statement. So we have 4 log base 4 of negative 3 times negative 70 over 3, and then minus 6, and this will be minus 3 out here. Let me make that better, and then we're going to say this equals 9. Okay, so starting on the inside, negative 3 times negative 70 over 3. We know that a negative times a negative is a positive, so let me just mark those out. And then 3 divided by 3 is going to be 1. So this becomes 70 minus 6, which is going to be 64. So you have 4 log base 4 of 64 minus 3 is equal to 9. Now again, you can go through and say, well, what is log base 4 of 64? A lot of you know that it's 3, but you can also use that trick that I just talked about in the last problem and just say that 64 is 4 cubed. And then log base 4 of 4 cubed, again, you can use that little shortcut. So log base 4 of 4 cubed. This by definition is going to be equal to 3. We'll see another special property where we can just do that. But the long way to do it is to say that the 3 comes out in front as multiplication, and then it's times log base 4 of 4, and log base 4 of 4 is 1, so this is equal to 3 times 1, which is 3. So lots of different ways that you can get that part of it. So this right here is 3. So you have 4 times 3 minus 3 is equal to 9. Well, 4 times 3 would be done first, so that's 12. And then minus 3 is equal to 9. And of course, 12 minus 3 is 9, so you get 9 equals 9. So our solution, which was x is equal to negative 70 over 3, is correct. All right, for the next few problems, we're going to change up the instructions. We want to sketch the graph of f of x and also g of x. We want to find the transformation from f of x to g of x. All right, for problem number 11, we have f of x is equal to log base 2 of x, and then we have our g of x. This is equal to the negative of log base 2 of x minus 2. So before we try to graph anything, let's think about the transformation that's going to occur from f of x to g of x. To do that, what I like to do is write things in terms of f of x. So I'm just going to write my g of x here is equal to, well, we see we have a negative out in front. So let me put the negative of, instead of log base 2 of x, I have log base 2 of x minus 2. So let me put f of x minus 2. Again, f of x minus 2 is just me plugging in x minus 2 for x right there. So g of x is equal to the negative of f of x minus 2. So that's how you could write it. Now, in terms of the transformation, you have this negative here, and then you have this minus 2 right here. So I'm going to think about those separately. First, if I think about the x minus 2 that's on the inside, remember this does the opposite of what you would expect. If you have x minus 2, that's going to shift me to the right by 2 units. So let me start by putting shifted. So shifted 2 units. And let me put right first before I put my comma. And then the next thing is I would think about this right here, the negative of, if you have the negative of f of x, that's creating a reflection across the x-axis. In other words, for the same x value, now you're getting the opposite y value. So let me put reflected across the x-axis. axis. So those are the two things that are going to happen. So a point on this first function f would be shifted 2 units to the right and then reflected across the x-axis to get that point on G. So let's come down here. I already made some tables, and this is a good way to graph things. I'm going to start with my f of x equals log base 2 of x. So we talked a lot about how to evaluate things, so I'm not going to waste a lot of time here. I'm just going to tell you what it is. So if you plug in a 1/2 for x, you're going to get a -1 for y. So log base 2 of 1/2 would be -1. Then if you plug in a 1 for x, you get a 0 for y. You plug in a 2 for x, you get a 1 for y. You plug in a 4 for x, you get a 2 for y. You plug in an 8 for x, you get a 3 for y. You plug in a 16 for x, and you get a 4 for y. Now, if we look at the graph, and this is going to be in, let's just call it red, f of x equals log base 2 of x. So this guy right here, we have enough points to sketch this guy. You might want some additional points going this way, but the way I do that is I think about the fact that, okay, this right here, I know it can't be 0 and it can't be negative. So what happens is the y-axis for that is going to be a vertical asymptote. So basically, this is going to approach where the x value is going to be 0, but it's never going to quite get there. Okay, so once you have this basic graph sketched and you have those points there, again, you can just shift your points around to get this graph right here. And let me just talk about that with the table first. So we know that basically we're going to shift, or let me put shifted 2 units right. Or actually, instead of writing this out, let me do a shorthand. So let me go right 2 units. And then I'm going to go REF for reflected. And then I'm just going to put X for x-axis. So basically, that's just going to change the sign of Y. So if you look at the x value here and the x value here, in each case, it's just increased by 2. So 1/2, if I add 2, that's adding 4/2. Let me do that off to the side because I know people can't do fractions in their head. So basically, I'm writing 2 as 4/2, and that would give me 1 plus 4 is 5, and this is over the common denominator of 2, so that's 5/2. And then the other ones, if you go 1 plus 2, that's 3, 2 plus 2, that's 4, 4 plus 2, that's 6, 8 plus 2, that's 10, 16 plus 2, that's 18. So I'm just increasing my x value by 2. Now, the given y value here is actually going to be changed into its opposite. That's coming from the reflection across the x-axis. So instead of -1, I get +1. So I'm just basically multiplying this by -1. Now, because 0 multiplied by -1 is still going to be 0, this is not going to change. Then 1 becomes -1, 2 becomes -2, 3 becomes -3, 4 becomes -4, so on and so forth. So that's how you can get your points if you want to use the table method. Or again, you could just go to the graph and just shift them like that. I'll just go through that with you in case you want to see it. So this point right here is 0.5, -1. Well, if I go 2 units to the right, I'm going to go right here. That would be 1.5. Then right here, that would be 2.5 in terms of the x value. Let me just put a little dot there temporarily. So right now, you'd be at 2.5, -1. Well, I'm going to reflect across the x-axis, so that's going to change my y value from -1 to +1, so that's going to give me this point right here. Then if I look at this point right here, which is 1, 0, I'm going 2 units to the right, and then because the y value is 0, well, I'm not going to change the y value because multiplying it by -1, that's going to leave it unchanged. It'll still be 0. Then if I look at 2, 1, I go 2 units to the right, so go to 3, then 4, so it'd be right there. And then basically, you'd have 4, +1, you reflect across the x-axis, you change that y value to basically -1, so now you get 4, -1. Just changing this from +1 to -1 in terms of the y value. Okay, for this 4, 2, well, now I'm going 2 units to the right, so 1, 2, that would put me right there. So the x value is 6, the y value is 2. Reflect across the x-axis, that puts me down here. This is 6, -2. Then this 8, 3, if I go 2 units to the right, 1, 2, now I'm going to be at 10, 3. Well, now if I reflect across the x-axis, I'm coming down here to 10, -3. Then if I look at 16, 4, again, go 2 units to the right. That's going to be right there. So that would be 18, 4. Reflect across the x-axis. That puts me down here at 18, -4. So that's how you can get this sketch right here. Again, you can just look at the points and just do the transformation with each point, and that will give you enough to draw the graph here. You can also do it with the table like we did on the other page. All right, for problem 12, we have f of x equals log base 1/3 of x, and then g of x equals log base 1/3 of -x, and then +1. So in terms of the transformation from f of x to g of x, I'm going to write g of x as being equal to, well, this would be f of -x. If I plug in a -x for x there, I would get this right here. Then you just have the +1. So what does f of -x do? Remember, that's now a reflection across the y-axis. So in order to get the same y value, when you have f of negative x, you need the opposite x value because you need to multiply by this negative here, or negative 1. So basically coming down here, let's go ahead and say that we are going to reflect, or I'll put reflected across the y-axis now. And this plus 1 on the outside, that's just going to shift me up by 1 unit. So let me put shifted up by 1 unit. Okay, so once again, I made some tables here. I put fewer points in. I think we kind of get the idea. If you need more points, you could just go through and get them. But if you have f of x equals log base 1/3 of x, again, if you plug in a 1/3 for x there, log base 1/3 of 1/3 would be 1. So you get 1 for the y value. Then if you plug in a 1 for x, you get 0 for y. If you plug in a 3 for x, you get negative 1 for y. If you plug in a 9 for x, you get negative 2 for y. Now again, if you look at the graph here, which is going to be this guy in red, so f of x equals log base 1/3 of x, again, x cannot be 0 and it can't be negative. So this guy is drawn to where it approaches an x value of 0, or again, the y-axis, that's going to be a vertical asymptote, but it's not going to actually touch it. Now notice that this guy, again, is going to be decreasing over the entire domain. If we go back to this graph right here, f of x equals log base 2 of x, this is increasing over the entire domain. So that's something we talked about in the lesson. When this base right here is greater than 0 and less than 1, we're going to be decreasing over the entire domain. If that base right there is greater than 1, we're increasing over the entire domain. So that's something to keep in mind. All right, so as we look at the points, we have 1/3, 1. So we're just going to say this is about 1/3 right there, and this is 1. And then this right here is 1, 0. This is your 3, negative 1. And this is your 9, negative 2. Okay, so that's our graph right there. In terms of getting this right here, let me come back to the table and do it this way first. Remember that we are reflecting, so let me put REF, across the y-axis, and then we are shifting up by 1 unit. Let me put U1 for that. So in terms of reflecting across the y-axis, your x value will now be its opposite, so 1/3 turns into negative 1/3. 1 turns into negative 1. 3 turns into negative 3. 9 turns into negative 9. And then you're shifting your y value up by 1 unit. So 1 turns into 2, 0 goes to 1, negative 1 goes to 0, and negative 2 goes to negative 1. So let's go back to the graph, and we'll do these individually, just in case you want to see it that way. So basically, if I start with this one right here, 1/3, 1, well, if I reflect across the y-axis, now I'm going to be, let's just say right here, hard to line it up because we don't have a notch. So basically you'd have negative 1/3, 1, and then you're shifting up by 1 unit. So that's going to be right there. So this is negative 1/3, 2 now. Then if you take this point right here, 1, 0, reflect across the y-axis, that's going to put me right there. So negative 1, 0, then I shift up by 1 unit, and that gives me that point right there, which is negative 1, 1. If I take this point right here, 3, negative 1, again, reflect across the y-axis. So that's going to put me right here. So that would be at negative 3, negative 1, and then shift up by 1 unit. That gets me right there, which is negative 3, 0. And then lastly, let's do this one. So we have 9, negative 2. I'm going to reflect across the y-axis. So I'm going to come way over here. That's going to be right here. So now I would have negative 9, negative 2, and then I'm going to shift up by 1 unit. That gets me that right there. So that's going to be negative 9, negative 1. Again, you can get more points if you need them, but I think this is enough to sketch both graphs. Okay, let's take a look at problem 13. So here we have f of x is equal to log base 2 of x, and then g of x is equal to 2 log base 2 of x plus 1, and then minus 2. Okay, so when we think about what's going on from f of x to g of x in terms of the transformation, again, I like to write things in terms of f of x. So you have, let's just start with g of x is equal to, let's go with the inside part first. So log base 2 of x is what we have here. Here we have log base 2 of x plus 1. So that would be f of x plus 1. You have this 2 that's multiplying that. So let me put that out in front. And then you have this minus 2 right here. Okay, so there's a few things that are going on. First, I'm going to start with this inside part here, this x plus 1. That is a shift to the left by 1 unit. Remember, if it's on the inside, it's always the opposite of what you're thinking. So this would be shifted. So shifted left by 1 unit. This one right here, this 2, that is multiplying this guy, that is giving me a vertical stretch by a factor of 2. So in terms of your y values, now you're multiplying them by 2. So that's all you're doing. So let's go ahead and say that there is a vertical stretch by a factor of 2. Then the last thing here is we're going to shift down by 2 units. That's what this minus 2 is going to do. So I'm going to put shifted, let me make this better here, down by 2 units. So again, you can make yourself a little table for each one. So f of x equals log base 2 of x. We did that in the first problem where we started this, so problem number 11. So we already know these points here. So for the x value of 1, we get a y value of 0. For an x value of 2, we get a y value of 1. For an x value of 4, we get a y value of 2. And then for an x value of 8, we get a y value of 30. So we know these points already. And we already know what this graph looks like. So here's my f of x equals log base 2 of x. So this guy in red. So again, it's going to approach where the x value is 0 or the y-axis. That's going to be a vertical asymptote because x cannot be 0 and it can't be negative. Then you have this point right here, which is 1, 0. That's actually going to be on both of these. You have 2, 1, 4, 2, 8, 3. We know we have 16, 4. And again, we can make more points if we need them, but this is enough for right now. So coming back, let's again think about what's going on. So we have this shift to the left by 1 unit. So I'm going to put L1. And then we have a vertical stretch. Let me put VS for that, by a factor of 2. And then we're going to shift down by 2 units. So I'm going to put D2. So when we think about the shift to the left by 1 unit, that's straightforward. The x values will just decrease by 1. So you have 1 here, 0 here, 2 here, 1 here, 4 here, 3 here, 8 here, 7 here. Very straightforward. These 2 steps here, that's going to create a little bit of confusion. Basically, you're multiplying the y value by 2 first, and then after you've done that, you're going to subtract away 2. So if I multiply 0 by 2, I still have 0. If I subtract 2 away, now I have negative 2. If I multiply 1 by 2, I get 2. Subtract 2 away, now I have 0. 2 times 2 is 4. 4 minus 2 is 2. 3 times 2 is 6. 6 minus 2 is 4. So that's where this is coming from in terms of the y values. So these 2 steps done in that order. Now, if you want, again, we can just go to the graph and look at each point and say, well, if I start with this one right here, which is 1, 0, well, I know that I'm going to shift 1 unit to the left. So let's say that puts me right there temporarily. Now I'm going to multiply that y value, which in this case, I'd be at the origin, right? I'd be at 0, 0. So I'd multiply that by 2. Well, 0 times 2 is still 0. Then I'm going to shift down by 2 units. So I'm going to subtract away 2 from the y value. So that puts me right there at 0, negative 2. So then if I look at this point 2, 1, again, I'm going to shift 1 unit to the left. So that's going to put me right there. And then I'm going to multiply that y value by 2. So basically 1 times 2 would be 2. So that's going to put me up here. Now at this point, I'm going to shift down by 2 units. So I'm going to go down right there. And this color is going to match, but I'm just going to go over it anyway. So that would put me at 1, 0. Okay, when I look at this point right here, 4, 2, again, I'm going to shift 1 unit to the left. So that's going to put me right there at 3, 2. I'm going to multiply that y coordinate of 2 by 2. So that would put me up here at 3, 4. Let me put this in here. This one's a little bit confusing. And then at this point, you're going to subtract 2 away from that 4 because you're shifting down by 2 units, and that's going to put me right there. Okay, let's move on to the next one. So now we have this 8, 3. Again, I'm going to shift 1 unit to the left. So that's going to put me right there. So now it would be at 7, 3. And then I'm going to multiply that y value of 3 by 2. So that's going to put me off my graph. Let's just say it's right there. Let's just say this right here. I'm just going to arrow to it. That would be 7, 6. We're just going to be there temporarily. Then we're going to shift down by 2 units. So we're going to take 6 and subtract away 2 from that. And that's going to put me at that point right there, which is 7, 4. Again, if you need more points to draw either one of these, feel free to add them in. But once you know the basic shape of your logarithmic graphs, you really don't need that many points to sketch something that's fairly accurate. All right, now let's change up the instructions again, and we're asked to find the domain. All right, for problem 14, we have f of x equals log base 5 of x squared plus x minus 20. So if you want to find the domain, remember that your argument for the logarithm needs to be positive. It cannot be 0, and it cannot be negative. So what we're going to do is say that x squared plus x minus 20 must be greater than 0. So you could go to Desmos and just make a sketch of y equals x squared plus x minus 20 and just look for where it's greater than 0. So in other words, for which x values am I getting y values that are greater than 0, or where am I above the x-axis in terms of the graph? But you can also solve it the old-fashioned way. So what we can do is just factor the left side here and say this is x and this is x. So this is a 1 here. So I need two integers that sum to 1 and give me a product of negative 20. That's really easy. It's going to be positive 5 and negative 4. So if you solve the related equation, so in other words, if you solve x plus 5, this quantity, times the quantity x minus 4, and you want to know where that's equal to 0, so you can get your critical values, where you do x plus 5 and set that equal to 0, you get x equals negative 5. So negative 5 is a critical value. And then you put x minus 4, you set that equal to 0, you get x is equal to 4, so that's another critical value. Let's put that like that. And basically you can just test. And you can do this really quickly. So things to the left of negative 5, is that going to work? Well, if I think about something like, let's just say negative 6 plus 5, that's negative 1. So this is negative. And then negative 6 minus 4, that's negative 10. So this is negative. Negative times negative is a positive, so that's going to be greater than 0. So this would be a T for true. Then if I think about between negative 5 and 4, we could pick 0. 0 plus 5 is 5, so that's positive. And then 0 minus 4 is negative 4, so that's negative. Positive times negative is negative. A negative is not greater than 0, so this would be false. Will not work. Then anything to the right of 4, that's of course going to work. Let's say you choose 5. 5 plus 5 is 10, that's positive. And then 5 minus 4 would be 1, that's positive. Positive times positive is positive, so that's always going to be greater than 0, so this is true. Okay, let me get rid of this, and we can just write our solution here. So we know that x is strictly less than negative 5. Remember, this is a strict inequality, so you're not going to put less than or equal to there. You want strictly less than. Then you're going to say the keyword or. You would say that x is greater than 4. Again, strict inequality here. So let me grab this real quick, and let me come back up here and just paste this in. So just solving this part right here, saying this is greater than 0, you get this right here. So what I'm going to do is write this out as a domain statement. So let me write that the domain, you could write it like this if you wanted to. So another way you could list this, you could do it in interval notation. Some teachers like it that way. So we're going to go from negative infinity, going up to and excluding negative 5. So we're going to use a parenthesis with negative 5 because it's excluded. And then you want the union with, you want anything greater than 4. So 4 is not included. Make sure you use a parenthesis there. This is going out to positive infinity. Then you can use your set builder notation. So if you want to do it that way, let me change the color up. I'll use this color here. So you could do the set of all x such that, and you just put this in here. So I'm going to go x is less than negative 5, or x could be greater than 4. So these are three different ways that you could write this. Now you can also go to Desmos and just verify this graphically. So you can key in f of x equals log base 5 of x squared plus x minus 20 and just look at the domain. So here you can see that for x values that are strictly less than negative 5, you'd be okay. And then here you can see that also for any x value that's greater than 4, you'd be okay. So let me write out another way to do this graphically for your domain. Well, this piece right here is where x is anything less than negative 5. Can't be negative 5 itself. So it would be x is strictly less than negative 5. Then or this piece right here, this is where x is strictly greater than 4. Again, can't be 4 itself. So x is greater than 4. Okay, for problem 15, now we have f of x equals log base 2 of x cubed plus 3x squared minus x and then minus 3. Okay, so thinking about this guy again, you want your argument here, which is this guy right here, to be positive. So it can't be 0 and it can't be negative. So we'll set up x cubed and then plus 3x squared and then minus x and then minus 3. We want to know where is this greater than 0. Let me make this better here. And let me grab this real quick. And let me come down here and paste this in. Now, you don't have to do it this way. I'm going to do it the slow way. You could do this graphically. So you can go to Desmos and just type in y equals x cubed plus 3x squared minus x minus 3. And you're looking for where this guy is greater than 0. So give me all the x values for which the y values are greater than 0 or we are above the x-axis. So you want this piece of the graph right here. This piece of the graph right here. And then you want this piece of the graph right here. So basically from Desmos or any graphing software, you could say that x would be greater than negative 3 and less than negative 1. So that's this piece right here. Or you would say that x is greater than 1. So that's the quick way to do it if you want to use a graphing calculator. Alternatively, we can just do it the slow way, just in case you want to see that or your teacher makes you do it that way. Essentially, you would factor the left side. Now, in this particular case, you can actually factor this using grouping. So I'm going to pull out and x squared. From the first guy, that would give me x plus 3. And the second group, I'm going to pull out a -1. That would give me x plus 3. And let me put for right now that this equals 0. We'll change it back in a moment. So if we factor out the common binomial factor, what you're going to end up with is this quantity x plus 3. And then times the quantity, you would have x squared, and then minus 1. And of course, this can be further factored. X squared minus 1 is x plus 1 times x minus 1. So let me put this equals 0. And I'm going to slide down here and do this on a different step. So x plus 3 times the quantity x plus 1 times the quantity x minus 1, and this equals 0. Okay, let me copy this. So x plus 3 times x plus 1, and then you have x minus 1. So those three quantities. Where is this greater than 0? Well, basically, you're going to solve this equation to get the critical values. So you're going to set x plus 3 equal to 0. You solve that, you get x equals -3. That's this guy right here. You get x plus 1, you set that equal to 0. You solve that, you get x equals -1. That guy right there. Then you put x minus 1, set that equal to 0. You get x equals 1, so that guy right there. We already know, because we looked at the graph, that the solution is going to be this guy right here and then this guy right here. So in other words, let me do this in a different color. This right here would solve that inequality. That would be your solution. But let's see if we can find this algebraically. Let me back out of these. Now, if you pick something to the left of -3, so you could pick -4, for example, if you plug that in each case, you're going to get a negative. So you'd have a negative, and a negative. So negative times negative times negative, you have 3 negatives. That's going to give you a negative, so that's not going to be greater than 0. So this right here, I'm going to put an F for false. Then between -3 and -1, that's where it's going to work. So what's going to happen is, let's just say you pick -2. Well, -2 plus 3 is +1. So this is positive. And then these are both going to be negative. -2 plus 1 is going to be -1. So this is negative. And then -2 minus 1 is -3. So this is negative. Negative times negative is positive. Positive times positive is positive. So this is true, right? A positive is going to be greater than 0. Let me get rid of this. And now here, in this region, you could pick 0. So that's between -1 and +1. Well, this would be positive. This would be positive. And this would be negative, right? 0 minus 1 is -1. So positive times negative is negative. A negative is not greater than 0. So this is false. This is not going to work. Then if you pick something that's greater than 1, well, it's going to be positive everywhere. So in other words, if you pick something like 2, this would be positive, this would be positive, and then this would be positive. 2 minus 1 is 1. So positive times positive times positive is a positive. So this would work. So this would be T for true. So algebraically, we can find that x is strictly greater than -3 and less than -1, or x could be greater than 1. So this is what we want. Let me grab this real quick, come back up here. So this would be your domain. Again, if you want to write it like this is fine. So this is the domain, and then you can also do it in interval notation. So if you want to write it that way, we can say this right here, you'd have -3 to -1 with both being excluded. And then you have the union with anything that's larger than 1. Again, 1 would be excluded. If you want to write this in set builder notation, let's do that. So let's put the domain here like this. So we would have the set of all x such that you're just going to drop this in here. So x is greater than -3 and less than -1, or x could be anything that's greater than 1. So that's how you would write that in set builder notation. Okay, so it's a good idea to go to Desmos and just verify this graphically. So here's your f of x equals log base 2 of x cubed plus 3x squared minus x minus 3. And again, for the domain, if you look at the graph, let me write out domain here. You're going to have this part right here, which is between -3 and -1. Both would be excluded. So let's say that x is greater than -3 and less than -1. Again, that's this right here. And then you'd also have, let me write the keyword or here, anything that's greater than 1. So it can't be 1 itself, but anything greater than 1, that's this piece of the graph right here. So x is greater than 1.